Hi everybody, hope that you're all doing well. It's been a little bit of time since we last met. Just had to get some things together so we could move onward. We're in the midst of Chapter 8, and just to give you a bit of summary of what we've done and where we are going. What we did in sections 8.1 and 8.2, we looked at 3 additional methods of solving a quadratic equation. The first method was the square root method. The second method was completing the square. And then most recently in 8.2 we talked about solving a quadratic equation by using the quadratic formula. And we looked at a couple of other minor objectives in 8.2. I won't summarize those right now because they're not critical to what we're going to be dealing with now. Now, as we move to 8.3, we're going to take these quadratic equations written as quadratic functions, and we're going to graph them. And in this first video, we're going to be describing some of the key characteristics of the specific graph of all quadratic functions, which are called parabolas. Now, in this video, we hopefully will be very clear about the things that I would like to get across to you, so that all of this package that we're going to put together is hopefully going to make some sense. We're going to start by going back to just a typical quadratic equation, and I'm going to show you the solving of that quadratic equation by using the quadratic formula. I want to let you know on this particular one that you're going to be seeing, the best method is not necessarily to use the quadratic formula. The best method would be to use factoring, because it would be done much more quickly than what you're going to see illustrated using the quadratic formula. But there's a reason why we're using the quadratic formula, and hopefully it will come to truth as we move through the ingredients of this video. So we're going to take a look at this rather small sheet of paper, and we're going to kind of zero in on this little paper, and let me kind of tell you what we're looking at here. We're taking the equation x squared minus 4x plus 3 is equal to 0, and I'm simply solving it using the quadratic formula. It's already in standard form. The value of a, which is the coefficient of the quadratic term, is 1. The value of b, which is the coefficient of the linear term, is negative 4. And the constant coefficient is positive 3. So I enumerated out those values, and then I plugged it into the quadratic formula, and doing all of the work as the camera is just being held on that, and just keep in mind that you can stop it and you can see the various steps that I've written down in this. We come to find out that the values of x that satisfy this quadratic equation are a positive 3 and a positive 1. And notice that those values of 3 and 1 are real number solutions. There are no imaginary solutions, because the value of the discriminant, as we can see right here, is positive. It's greater than 0, and it happens to be a perfect square. So, like we had pointed out when we were dealing with the discriminant, if the value of the discriminant is a positive number and it is a perfect square, there will be 2 rational real number solutions. And one of those rational solutions is x is equal to 3 or x is equal to 1. Now, we're going to move into 8.3 now and get into the whole idea of graphing a quadratic function. And so I wanted to start with this little diagram first. And now we're going to make this statement, which I have written right in here. If the solutions of a quadratic equation are real number solutions, that doesn't mean that they have to be rational. They can be irrational conjugates as well. But as long as they are real number solutions, solutions that can be represented on a number line. Now let me get a little bit more current. Solutions that can be represented on the x-axis of a coordinate plane. The real number solutions of a quadratic equation correspond to the x-intercepts of the related quadratic function f of x is equal to x squared minus 4x plus 3. You see, this quadratic equation right here is not written as a function. It's just merely written as an equation. And we came to find out down here that it had two real number solutions, positive 3, positive 1. But now as we move into 8.3, the real number solutions of this equation correspond to the x-intercepts of the related quadratic function f of x is equal to x squared minus 4x plus 3. Notice this trinomial is the same identical trinomial that was a part of this quadratic equation. But notice it's being written in function notation. We now have a quadratic function here, and we should know that f of x means the same thing as y. So now we're going to pull away from that little chart, and we're going to move over to the actual graph of the quadratic function f of x is equal to x squared minus 4x plus 3. And notice, back over there on that original sheet of paper, the real number solutions of that equation were positive 3 and positive 1. And then I've said, and now I'm saying it for the third time, those solutions of 3 and 1 happen to correspond to the two x-intercepts that happen to be two critical points on this overall graph, which happens to be called a parabola. This point right here, the point 3, 0, has an x value of 3. That x value of 3 happens to correspond to one of the solutions of that quadratic equation that we just came from. And the other x-intercept, 1, 0, the x value of 1, was the other real number solution of that quadratic equation. So the real number solutions of a quadratic equation happen to correspond to the two x-intercepts that same quadratic function has. One of them in this case was the x-intercept of 3, 0, and the other was the x-intercept of 1, 0. Now, let's talk about this graph that we see placed up here on this x and y axes that we see. Item number 1. Let's define the word parabola. A parabola is a bowl-shaped curve that either opens upward, such as this one, or it opens downward, such as this little example that I just kind of pointed out right here. Now, how it opens up is based on fact number one that you're going to need to make sure that you memorize and that you know. How the parabola opens either upward or downward is based on the coefficient of the quadratic term, the variable a. The parabola will open upward if a is positive. It will open downward if a is negative. So how a parabola opens, upward or downward, is hinged on the fact of the coefficient of the quadratic term of the quadratic function. It hinges on the value of a. If a is positive, the parabola opens upward. If a is negative, it opens downward. Now, this function right here, f of x is equal to x squared minus 4x plus 3. Let's look at the coefficient of the quadratic term, which is our a. The value of a is 1. 1 is positive. That means that the parabola is going to open upward. And this happens to be the parabola for this quadratic function. So that's what we mean by a parabola. Item number 2, in terms of the characteristics of a parabola, is the vertex. Now, what I'm about to say right here is not in print on this sheet of paper, but I'll mention it initially. The most important point on the parabola, it is the most critical point of the entire graph. It's called the vertex. The vertex is the turning point of the parabola. Notice this parabola. This is this bowl-shaped curve that in this case happens to be opening upward. The turning point of this parabola is, in this case, this point right down here at the bottom. It's the point at where the graph makes a turn. It's turning upward, moving on this right-hand side. It's turning upward, moving on this left-hand side. This point right down here at the very bottom of the graph is called the vertex. If the parabola opens upward, the vertex happens to be the lowest point of the graph. The vertex is the lowest point of the graph if the parabola opens upward. If it opens upward, the vertex is the lowest point on the graph. And in this graph right here, the vertex happens to be the point 2, -1. Don't worry about that ordered pair yet of 2, -1. Just be concerned about the fact that we recognize that the vertex is the turning point of the parabola. And if the parabola opens upward, the vertex is the lowest point on the graph. If the parabola opens downward, the vertex happens to be the highest point on the graph, and I noted that here. If the parabola opens, if it opens upward, it's the lowest point, and it's the highest point of the graph if the parabola opens downward. This is downward. There's your vertex. It happens to be the highest point of the graph. That's what we mean by the vertex. A third characteristic of the parabola is this. The parabola is a very unique looking curve. It happens to be a symmetrical curve. And I'll kind of key in on that word symmetrical in a minute. If you take an imaginary vertical line, vertical, and you send that vertical line straight down through the vertex, that imaginary vertical line is called the axis of symmetry. The axis of symmetry is a mirror line through the vertex that divides the parabola in half. This mirrored line right here, you can see that it's dotted. It's not part of the graph. It's an imaginary vertical line that intersects or cuts straight through the point of the vertex. And what that vertical line does is it cuts this entire parabola exactly in half. In half meaning this. If I were able to take this side of the parabola and fold it, crease it along this imaginary axis of symmetry. If I creased it along this dotted line right here, each and every point on the parabola on this left-hand side would, when it is folded over against that axis of symmetry, every single point on this half of the parabola would have a matching point on the other side. That is what we mean by the axis of symmetry. Again, it is not part of the graph. It is an imaginary vertical line that cuts through the vertex and splits the parabola exactly in half. Now, I'm going to talk specifically about this graph, this parabola, for the graph of f of x is equal to x squared minus 4x plus 3. I want you to pinpoint and notice some key things with me on this graph. First of all, these x-intercept points, I'll start with these. This x-intercept point is 1, 0. Its mirrored point on the other side of the parabola is the other x-intercept, 3, 0. I want you to notice something about these two mirrored points. We call them mirrored points because if this point right here, 1, 0, were able to actually turn itself to the right and look directly across the axis of symmetry, it will find its mirrored point on the other side. It would find it. They reflect off of one another. They're mirrored points of one another. And I want you to notice something about that first pair of mirrored points. Look at the y values of each one of the mirrored points. They happen to be the same. Let's go up the parabola to the next pair of mirrored points. This point is 0, 3. X is 0, 1, 2, 3, y is 3. Its mirrored friend over on the other wing of the parabola is identified by the ordered pair 4, 3. Would you take a gander at the y values of those two mirrored points? He's 3 and he's 3. They're the same. And then one more pair just to take a look at, all the way up here to the top. This point on the left side of the parabola is identified as negative 1, 8. Its y value is 8. Its mirrored point over here in quadrant number 1 has the ordered pair 5, 8. Look at the y values of that pair of mirrored points. They're the same. So, If that occurrence happened 3 different times, there must be several different mirrored points. If I can just use my hand for a minute, my fingers, there's an infinite number. There's an infinite number of mirrored points that just keep going out and out and out. There's an infinite number of them, and we can say this truth about every one of the mirrored points on that graph of that function. The y values of any pair of mirrored points will be the same. That is a truth. That's going to be key. Just keep this in mind. That's going to be key in the next video that we'll do when we actually get down to the business of graphing a quadratic function. I'm just detailing some key things right now, and I need to. That's one key truth. Now, let's come back down to those 2 x-intercepts. And let's talk about the x values of each of the mirrored points. Now, when you look at the x values of each of the mirrored points, obviously the first thing that you find out is they're not the same. And you're just going to look at them and probably think, unless you already know about this, but if you don't, and a lot of people don't know about it, they're not going to see any relationship necessarily between the x value of 1 and the x value of 3 for that pair of mirrored points, the x value of 0 and the x value of 4, the x value of those mirrored points, the x value of -1 and the x value of 5, the x value of the uppermost pair of mirrored points. But I am here to tell you there is a relationship that can be garnered if we do something very, very specific to the respective x values of any set of mirrored points. I want you to come down to the vertex. Kristen is holding it right here. I want you to look at the x value of the vertex. The x value of the vertex for this quadratic function is 2. Let's go up to this first pair of mirrored values, and now I'm going to tell you a truth. There's a relationship between the x values of any pair of mirrored points, and here's the relationship. I'll say it slowly. If you take the x values of any pair of mirrored points on a parabola and you find their average, how do you find an average? You add up the numbers in the set and you divide by the number of items in that set, and that'll give you an average. We have one x value here of 1, and its mirrored brother on the other side has an x value of 3. There's 2 items in this little set, an x value of 1 and an x value of 3. Those are the x values of this pair of mirrored points. If we find the average of these 2 x values, the 1 and the 3. Now that's not going to take an Einstein to do it. We'll just talk it right now. If you take 1 and you add it to 3 and you get that total, which is 4, and you take 4 and you divide it by the number of items in the set. There were 2 items in the set. One of the numbers was 1, the other number was 3. 1 plus 3 is 4. If we take 4 and we divide it by 2, what do we get? 2. And that 2 just happens to match the x value of the vertex. And we're going to find out in a moment. It might sound coincidental. It is not. Let's go upward to the middle pair of identified mirror points here. Let's take the 2 x values and add them up and divide by 2. Let's get their average. That x value is 0 for this point. This x value is 4 for the counter mirrored point. Those are the mirrored points. 0 plus 4. 4. If we take 4 and divide it by 2, 4 divided by 2, 2. The uppermost one. Take the x value of -1 and its mirrored friend, the x value of 5, and add 5 to a -1. 5 added to -1, 5 plus -1, 4. 4 divided by 2, 2. The x value of the vertex. Now, folks, if we found the x value of 2 from that pair of mirrored points, that pair, and that pair, it would happen with any pair of mirrored points. It is not coincidental anymore. So, the last little segment that I want to share in this initial video is, I've already told you that the most critical point of being able to come up with the parabola is to be able to identify the vertex first. The vertex must be identified first. You don't get any of these other points here. You don't attempt to find any of these points on this right side or any of these points on this left side until you find the turning point of the graph. The vertex is the most important point of the parabola, and we need to get it first. How are we going to get it? We're going to get it by finding the x value of the vertex first. Once we find the x value of the vertex, we'll be able to very easily find the y value of the vertex by evaluating the function. But we have to come up with the x value of the vertex first. And right down here in the lower left-hand corner of this sheet of paper, we're going to come up with a formula to find the x value of the vertex. Now, I started off with this guy right here. When I started off with this video, we solved this quadratic equation. That was a 0 then. We solved that quadratic equation by using the quadratic formula, which is the opposite of b plus or minus the radical of b squared minus 4ac over 2a. When we used that quadratic formula, that gave us the two real number solutions that happen to correspond to these 2 points right here. The x-intercepts of this parabola. Would you look at these 2 points again? They're mirrored points. They bounce off of one another. What did we do with those 2 mirrored points to find the vertex? We added their x values together and we divided it by 2 and we got the x value of the vertex. I want you to look at this quadratic formula right here. One of its intercepts up here, one of them, is going to be this guy right here. The opposite of b plus the radical of b squared minus 4ac over 2a. This one right here. One of those x-intercepts is going to be found by evaluating this guy. The opposite of b plus the radical of b squared minus 4ac over 2a. That would give you one of those intercepts. Let's say him. It doesn't matter which one. It'd give you one of them. The other one. The other intercept will be gained by this. The opposite of b minus the radical of b squared minus 4ac over 2a. This gives one of the intercepts. This gives the other one. Let me point it up here, because I don't want you to be lost. this expression right here, it gives us one of these intercepts. Let's say him. This one right here will give the other intercept. Now, they're mirrored points. How do you find the x value of the vertex? You add those x values together and you divide by 2. That's what we're going to do right here. Now, I do not want you looking at this saying, hey, you're going to lose me here, or you've already lost me. No, I'm not going to. If we take this expression and add it to this expression right here, in other words, if we add this x-intercept, which is what it is, with this, the other x-intercept, they're the mirrored points. If we add those two together and divide it by 2, that should give us a formula for finding the x value of the vertex. Why am I using that? Why am I using that formula right there? Why am I using the quadratic formula? Because I need to generate a formula for the x value of the vertex. I can't generate a formula by using numbers. I have to use algebraic expressions. This is one of the intercepts. This is the other x-intercept. How do we get the vertex? We add the two x values of a pair of mirrored points, which are these two, and we divide it by 2. Now, look up here in this numerator right here. We're going to add these two together. And a lot of things are going to cancel out. Notice this negative 1b, this negative 1b. We're going to add it with this other negative 1b right here. Just backing up a second. I don't have to find a common denominator. The denominators are the same. I'm adding these two. Don't worry about him yet. I'm adding these two. Negative 1b added to another negative 1b is a negative 2b. This fella right here. Right there. Look at the radical part. This is a positive radical of b squared minus 4ac, and this is a negative radical of b squared minus 4ac. These two cancel. They cancel out. They actually cancel out. So the only thing that we have for our numerator is a negative 1b added with a negative 1b, a negative 2b. And we're going to divide it by the common denominator of 2a. So a negative 2b over 2a, that's actually the sum of those two x values, of those mirrored points. The sum is negative 2b over 2a. Now we're going to divide it by 2. So I showed it in this way, divided by 2 over 1. Then I came down and I brought down the negative 2b over 2a, changed the division to multiply, and reciprocated the 2 over 1 to 1 over 2, and I reduced. I canceled out these 2's right here. And if we multiply across, we'll have a negative 1b, or the opposite of b, over 2a. And I'm here to tell you, if that just drifted right over your head, you can pause the tape, you can rewatch it, but the nitty-gritty is right down there in the cloud. The formula for the x value of the vertex is the opposite of b over 2a. You'll have to memorize that little puppy. You're going to have to memorize him, just like you're going to have to memorize a few other things that are on here. The x value of the vertex is equal to the opposite of b over 2a. Now when we get to the next video, when we get to it, we're going to actually begin with a quadratic function. And we're going to graph it. And the very first thing that we're going to do when we look at that quadratic function, the very first thing that we're going to do, even before the vertex, we're going to define how that parabola is going to open. It's either going to open up or it's going to open down. And we're going to make a little note on the board so we'll know exactly what it's going to do and how it's going to open. But then we're going to find the vertex. And the starting point of finding the vertex is getting the x value of the vertex. And to get that x value of the vertex, if for one more moment Kristen will just show it, the x value of that vertex, we're going to follow that formula, the opposite of b over 2a, and that's going to give us the x value of the vertex. Don't worry about getting the y value of the vertex. We're going to get it. And it'll be nice and easy to get the y value. But we've got to have something to hold on to get the x value of that vertex. And we've got it. Now I hope you caught just a little bit of that. I know this was a time-consuming video, and I hope I don't lose it. Now you take care of yourself, and we'll join you together again, and we'll get to the graphing of the quadratic functions. Bye-bye for now.